Hello and welcome back. In section 5.4 we get into logarithmic functions. So we'll start with a basic definition. If b raised to the p is equal to c, so a base to a power equals some constant. Two rules for b. b is greater than 0 and b is not worth 1. Then the log base b of, and the other two things just trade sides, of the constant is equal to the power. So on this one, the domain for c, notice b is a positive. So positive to a power is still positive. So c has to be positive. So a few just basic translations. If we have 8 cubed is equal to, say, k, then the equivalent logarithmic notation, so this is exponential. The equivalent logarithmic would be the log base of the exponent is now the base of the log, so log base 8 of the other two trade sides of k equals 3. If we have b to the 5th is worth 19, then the equivalent in logarithms, log base b of 19 equals 5. A couple special cases, e to the c equals 20. If the base is e, the log base e is defined to be the natural logarithm written as ln. So natural log of 20 is equal to c. Another special case, 10 to the m is equal to x. If the log is base 10, that is written just then as a log. So they would just write this as log of x equals m. And of course, we don't always just start with exponential and go to logarithmic. We will work the other way as well. So if we're given log base c of 15 is equal to 9, then an equivalent exponential expression would be c to the 9th power is equal to 15. If we're told natural log of k equals r, then the equivalent in exponential, my base is e, so e to the r is worth k. If we're told that the log of 105 is equal to, let's say, n, then 10 to the nth power is worth 105. So make sure you're doing some practice on translating back and forth between exponential and logarithmic. You should be able to start with one and get it to the other one each time. So next we look at getting exact values without a calculator. So this involves basically putting in a placeholder variable. Log base 5 of 125. We just use a little let line. Let log base 5 of 125 equals some number. And in this case, we would just translate it. Okay, 5 to some number is worth 125. So it's asking, okay, what power would I raise 5 to hit 125? That would be the third power. I want the log base 2 of 32. Again, I can let it equal some placeholder variable. So 2 to some power is 32. Well, 32 is 2 to the 5th, so our power has to be 5. If I have the log base 3 of 1/81st, again, I'll just put in a temporary placeholder variable. So 3 to our power is worth 1 over 81. 1 over 81. 81 you might recognize as 9 squared. 9 squared is the same as 3 to the 4th, since 9 is 3 squared. 3 squared squared is 3 to the 4th. So 3 to the x is 3 to the negative 4th. So our missing number was a negative 4. No calculator needed. As far as x's and y's go, if we start putting these into the two-dimensional plane, we have y equals b to the x, usual rules for b, as they've been throughout chapter 5. B is positive and not worth 1. Our domain, can't miss. Pick a real number. You can take a positive number and raise it to that power. A range, though, positive number to a power is going to stay positive. So I can get close to 0, but I won't reach there. This also brings up the idea of the inverse. So in the section on one-to-one functions, we looked at the idea of the inverse. To make an inverse function, remember x and y trade roles. Then we just solve for y. So this one, it's in exponential. We'll translate it to logarithmic. So then the log base b of, and the other two things trade sides. So b was on the same side as y, so it's the x that's now on the same side. Log base b of x is equal to y. And remember, if x and y trade roles, that means domain and range also trade. So my domain for this guy is 0 to infinity, and our range is all the real numbers, negative infinity to infinity. And we can actually use that to sketch graphs of logarithmic functions. So we'll start with y equals log base 2 of x. So our first one will graph 2 to the x power. And here, I'll just use my stamp for time's sake. So 2 to the 0 is 1, 2 to the first is 2, 2 squared is 4, 2 cubed is 8, 2 to the fourth is 16, that's off our grid. Moving the other way, 2 to the negative first is a half, 2 to the negative second is a quarter, then to an eighth, a 16th, a 32nd, and so on. So we have this horizontal asymptote of y equals 0. So we'll connect those guys up with a smooth curve, arrows on both ends. So then to switch that over, these two are inverses of one another. So every xy in y1 is now a yx in y2. So for example, we went through 0, 1, now we have 1, 0. We went through 1, 2, now 2, 1 is a point. We had 2, 4. Now we've got 4, 2. We had 3, 8. Now we have 8, 3. Instead of -1, +1 half, we have +1 half, -1. Instead of -2, +1 fourth, we have +1 fourth, -2, and so on. So now it shouldn't be too surprising that our y equals 0 asymptote is now an x equals 0 asymptote when we did the inverse. So same deal, we connect those up with a smooth curve, arrows on the end because the pattern does continue. And notice they are symmetric about the identity function. If we sort of folded this in half on a 45-degree angle, the points would land right on top of one another. And occasionally they'll give us one where we get to do a little bit more shifting around and such. If we want to graph, let's say f of x is the log base 3 of x minus 3. So y1 is going to be 3 to the x. And then we'll use the idea of the inverse function again. So 3 to the 0 is 1, 3 to the first is 3, 3 squared is 9, 3 cubed we would be all the way up at 27. 3 to the negative first is 1/3, 3 to the negative second is 1/9, 3 to the negative third, 1/27, and so on. So there's our asymptote again, the dotted line at y equals 0. So then I'll do the inverse, which would be log base 3 of x. So each of those ordered pairs, I just graph its partner. So 0, 1 is now 1, 0, 1, 3 is now 3, 1. 2, 9 is now 9, 2. -1, +1/3 is now +1/3, -1, and so on. So now we have this vertical asymptote at x equals 0. And our last step then, we have the -3 outside. That's just going to drop all of these points down 3 units. So notice on this one, our vertical asymptote did not move. Had we had some shifting within here, we could have shifted it left or right, depending on what was happening on the function. All right. Last thing we'll do is, in this section, is look at solving some of these. So log base 5 of x is worth 2. So this x is inside of the argument of a logarithm, so I'm going to have to turn it into an exponential to solve it. So the base stays the base. The other two things trade sides. So 5 squared is equal to x. So x is worth 25 on that one. They could tell me that e to the negative 3x is worth positive 1/4. Variable is inside of an exponent. I'll need a logarithm to get it out. Base is e, so this would be a natural logarithm. So natural log of 1/4 is worth -3 times x. And we divide both sides by -3. So x is natural log of 1/4 divided by -3. I can't do anything with the 1/4 and the 3. The 1/4 is part of the argument of a logarithm. The -3 is just a number by itself, so I can't do any reducing. So just watch out for, even if you have something like the log base b of 15 divided by 3, there's no reducing that can be done with this. I cannot touch the 15 and the 3. Does not equal log base b of 5. Cannot do that. So next one, log base 4 of 4 to the x. So sometimes we have a logarithm that has an exponential within the argument. That's okay. That happens sometimes. So our base stays the base. Other stuff trades sides. So x is worth -1 here. All right, so that should give you enough ammo to take a look at some of the 5-4 problems. So I would recommend 1 to 10 all, 11 to 111, every other odd. So do 11, skip 13, do 15, skip 17, and so on. If you have any questions, please get in touch. Otherwise, I will see you next time. Stay safe out there.